Hey, students, I thought it would be helpful to have a solution. And so I hope you will have some time to kind of go through this. It might be a good learning opportunity for you. So try to do both of those. Try to kind of go through and learn from your mistakes. And then at the same time, try to get an idea of what mistakes you did make. And you'll have a kind of a rough idea of your score. And then when you get your score, you'll have kind of a rough idea of why you missed some points here. All right. So let's try number one here. It says a block of mass, and it gives the mass here, and it hangs from the ceiling, has two springs, a K1 and a K2. And after hanging in equilibrium, the block is then lifted up a little distance, keep that in mind, and then released with a small upward speed. So I guess it would kind of look like this. If the pin was the block, I'd kind of like lift it up a little bit. When it gets here, then I'd give it a little nudge upward, and that would then start the oscillations. And so keep that in mind, because B asks for the amplitude, so it's going to be more than the 3.25 centimeters. It's going to be, you're going to be lifting it up and then give it a little nudge upward, and it's going to do this kind of thing. And that's, anyways, what we're asked to do. So you'll see that part A, B, and C kind of get progressively harder. We'll start with the easy one, A. It asks for the period, and the period is 2 pi divided by omega. And if you remember working these out in class, omega is the square root of m over k. And if you remember the two springs in parallel, the equivalent, so I'll put the equivalent here, or the effective spring constant, is the two added together. And so 85.5 plus 68.3. And you can now think for the rest of the problem as this being a mass on one spring with this added spring constant. And of course the mass is the 2.54. So grabbing my calculator here, I'll add them together. 85.5 plus 68.3. Maybe I'll make a little note. I don't know if I'm going to need the total spring constant. Oh yeah, I think I will in B. But I'll just say, okay, that's what those two add together. Divide it by, maybe I'll just put the effective spring constant. So for the rest of the problem, I'll just think of it as one spring, the spring constant of 153.8. Divide that by 2.54 and take the square root, and I get then an angular frequency of 7.78 radians per second. And then that would give me a period of, so 2 pi divided by the last answer, and it looks like about 0.807 seconds. Okay, so there's A. What is the period? Now B says what is the amplitude. So again, as I said, if this is put on the ceiling and comes down to equilibrium right here, then you grab it and you kind of lift it up and then give it a nudge so it does this. The amplitude is going to be greater than, and that's kind of this hint here, it is not 3.25, and it is best done by conservation of energy. So remembering our principle of conservation of energy, maybe we'll do this. Why don't we talk about the energy it has right as you release it? So as you push it up, it has a little potential energy. And if you give it a little nudge, it has then kinetic energy. Now, in case you're wondering about the gravitational potential energy, the MGH, Keep in mind, one thing we learned about vertical springs, if you remember in this, we solved horizontal springs first. And of course, in that case, we didn't have to worry about gravitational potential energy or the gravitational force. And then, when we got into the vertical spring, we at first thought about the force from the spring and the force of gravity, and then realized that the extra force of gravity was counterbalanced by the extra stretching to a new equilibrium position. And so for the vertical spring, without repeating too much of the vertical spring, but for the vertical spring, we said the force from the spring was a minus kx, where x was made out of two pieces. The first piece is the really stretching of the spring to a new equilibrium, and then this is the stuff beyond. And then when you combined it with the force of gravity for net force, the two canceled off in equilibrium, and you only had to worry about how much did the spring stretch from the equilibrium. And so, in other words, we could ignore the force of gravity and therefore also ignore the energy associated with gravitational potential. It's buried in that extra stretch. So as long as we measure all of our x's from equilibrium, the nice thing about a vertical spring is we could treat it without any gravity. So keeping that principle in mind, I could just say that there is a potential energy and a kinetic energy when I release it. And I don't need to worry about an MGH. I don't have to worry about any gravitational potential energy because I'm going to measure zero from the equilibrium spot. And that's kind of the beauty of it. And in fact, the reason this can be helpful to solve for the amplitude is because this is the total energy when you release it. So kind of looking at a picture again, kind of nudge it up and give it a little kick upward. At that point, it has a displacement from equilibrium, so it has a potential energy, and it also has a little nudge, so it has a kinetic energy. But eventually, it is going to go up to its full amplitude, and at that point, its displacement is its amplitude, and its kinetic energy is zero. So we can use this information when we nudge it, its position and its velocity, to get its total energy, and realize that that's the total energy it's going to have later on when it gets all the way up to its full amplitude. And that's how we can solve for amplitude. And so what I'll go ahead and do is, maybe to make the math a little easier on me, cancel off the 1/2. And also, maybe I'll move the k over here, so this just becomes an x squared, and this over here becomes an m over a k, and then a v squared. Because the k over m is this omega. And so I've already calculated it, although I can also just plug it in. And maybe I'll just plug it in. But I was going to do something clever and then use that. And yeah, I'll just get the A now. Okay, so using this conservation of energy and this formula, my original lifting up, and I'll do it in meters, is 0.0325 squared. I'll add to it, here's the mass, 2.54 divided by the K, 153.8. And then that velocity that I nudged up, 0.24 squared. And that should be the amplitude squared. So if I take the square root of that, I get an amplitude of 0.0448 in meters. And if you want, you can write that as 4.48 centimeters. Either is perfectly fine. And then on to the harder one, I think the hardest one, although it's not too much math here. It's really given the equation of motion. And so giving its position, you need its amplitude. Well, that's where B comes into play. So I'll put 4.486 centimeters. And then cosine, here's the omega, which we solved earlier as 7.78 t. And then the part that's going to make it a little bit of a challenge is this initial phase. We know it's not 0 because a 0 would mean, well, let me just draw a cosine function. A cosine function looks a lot like this. And so if this is x and this is t, a pure cosine function with no phase would start at its maximum and head down. And that's not what we have. That's what you would have gotten if it just said you lifted it up and then you let it go, and then it would go back and forth, meaning it would have started at its highest point and then gone back to equilibrium and then gone negative. And that's what this graph is. So we know phi is not equal to 0. And in fact, we know it's not one of the easy ones like a pi or a 2 pi or a negative 2 pi or a pi over 2, because again, that would be like a sine function. That'd be something that if it started here and instead of lifting it, you just kind of tapped it, it went boing and back and forth. So that'd be like a perfect sine function. So it's not that. What it is, if we look at this graph, it says that it's upward at 0.3. So if the full amplitude is this 4.48, maybe in my diagram, 0.325 would be right here. And so it would be starting here. Although that would be the wrong one because it also says that it has an upward speed. And, of course, the slope of a position is its speed, and this slope is downward. So this would have been the answer if you had kind of lifted it up and then kind of dragged it down to begin with. And that way it would have an upward position and a downward speed. But that's not what this problem says. This problem says you lift it up and then you give it an upward push. So we're looking at this phase. Of course, the cosine function goes to negative here. And so this position is the same as that one. And that has a positive slope. And so these two differ by 2 pi. So we need to find either a small negative number or a big number that's just a little bit short of one full cycle. So this 2 pi is a full cycle, but we can write it as that one, or we can write it as that one. So let's do the calculation, and maybe the easiest thing to do is to write out the equation at time equals to 0, because we know its position is 3.25. So there's the position. And I'll repeat the amplitude when time is 0. And that's a perfect equation since the only unknown now is phi. And so grabbing my calculator and checking that I'm in radians mode, okay, let me do the math here. So let me take the 3.25 and divide it by the 4.48. So that's the cosine. Now let me do the inverse cosine of that answer. And it looks like I get from my calculator a 0.759 for the phase. Now, one thing we got to kind of remember from our trig class is these cosine functions repeat, and that's what this picture is showing. There would be two places in a cycle, here and here, or here and here if you want to do the negative value, where the cosine function actually equals 3.25. And calculators only give us the answer in the first quadrant. So this answer is the wrong one. It is this one. It doesn't represent the negative speed. Now, by the way, I suppose you could just also take the derivative of this and set it to the equal speed and get the two angles, and you'll see that there'll be two answers here for the cosine, and then there'll be two answers for the sine, and only one pair matches, and that must be it, which would be the negative. But I can just see from the picture that the cosine function would be either a plus or a minus if I use that as the answer. Or I can go 2 pi minus that much. But I think I'll just do the negative. And so my point is this trig function has two answers, and the one I want is the negative one. And so phi is a negative 0.759. And then that finishes part C. So the total answer here would be 4.48 for the amplitude. Cosine, 7.78 for the angular frequency. And an initial phase of negative 0.759. Now, like I said, I'm just out of curiosity. What if I go 2 pi minus the last answer? And 5.52. So you could use this one right here, 5.52. So if you wanted to say plus 5.52, that works too. I suppose you could even write it as a shifted sine wave, but probably didn't. I was going to maybe work that out, but that's probably a waste of time because I put cosine in there, so I think you guys all did this cosine functions. Oh, by the way, then, maybe changing to another color here. Yeah, grab the green one here. You, of course, probably remember me saying this many times, that if you have a function and you want to shift it by a certain amount, right, you go minus that amount. And so what you're really saying here is this red one I drew is a normal cosine function without a shift. This one, then, is now a cosine function with a shift of that much. So if you can imagine kind of picking up this cosine function and sliding it forward by 0.759, this point would become right there, and you would have something that would look like this. Oops, bad picture. Yeah. And so right there at time equals to 0, we have an upward displacement of 3.25, and we have an upward slope, so we have an upward small speed of 0.249. So as you can see, there's not much math in part C. It's just, hey, write out what you do know, and then the only thing you don't know is phi, and solve for phi. But understanding why you would do that, and then also understanding why you would pick the minus sign, not the plus sign, because you can get kind of lazy and just take whatever the calculator gave you and not think about the math, and you might end up with a plus sign here. Anyways, there is the hard one for part 1. Although on the test, I think the hardest one is part B of number 2. Okay, so hope that helped, and let's move on to number 2 here. Okay. So number 2 says we have a large crane. It's holding this big bag, trying to give a little picture here. It's with a single cable. I tried to put a little note here because the only picture I could find had a real cranes often have multiple cables so you can get more leverage, and I couldn't find one with a single cable. But the problem's much easier with a single cable, and that's what I wanted to give you here. So single cable. We have a full bag of seawater, and it's 1,000 kilograms hanging here. The cable has a small amount of mass. And then a nice little hint that we did in the problem, and that is the cable is light enough that when it comes to the tension in the cable, you really only have to worry about the load you're holding. You don't have to worry about the weight of the cable. And I felt like I needed to throw that in there because I know we had a really good homework problem, 2 of them I think actually, where you had to include the weight of the cable as part of the tension, and so the tension changed because if you, on the side here, had a ceiling or something, and you have a cable and then a heavy weight, this part of the cable has to support not only this heavy weight, but also the weight of the cable below it. And so the tension up here is actually a hair more than the cable, or than the tension down on the lower part of the cable, depending on how much the cable weighs. But for most objects in practice, the object you're holding is way, way more than the mass of the cable. And so the difference in tension between these 2 spots is minor. And although it's a fun calculation, and that's why you did it on the homework, but not here on the test. So what we can do then is safely say that the tension all the way through the cable is the same, and that it is equal to this weight. And so the free body diagram would be gravity pulling down the load, mg, and tension pulling it up. And the sum of those 2 have to equal to 0. And so the tension is equal to the load only. And that, of course, is 1,000 kilograms times 9.8, which makes 9,800 newtons for the tension. At least until we get to B, and the water starts leaking out of it, okay? But here, see, the cable is light enough, that you can ignore it. All right, because you can see 25 meters of cable, and at a half a kilogram a meter, it's only going to be about 12.5 more kilograms. That's minor compared to the 1,000. And so what it says here is a little wave pulse is made. How long does it take to travel down? Well, I'm kind of hoping that you recognized that it would be a constant speed because it's a constant tension, at least until we get to B. And so this is going to give us a velocity of, and so I'll put the tension of 9,800. Yeah, I'll put the mass density of 0.5. Well, let's grab the calculator here. So 9,800 divided by 0.5, taking the square root of that. And we're looking at a speed of about 140 meters per second traveling down the cable. And then going back to our Physics 121, we know, distance is equal to, and I'll just put the full formula here, but for something this simple, There is no acceleration. We'll call the initial position 0. And so distance equals velocity times time, or put another way, time is now the distance traveled divided by the velocity. So the 25 meters divided by the 140 meters per second is going to give me the 25 divided by 140. And it's a short amount of time of 1.79 seconds. So about a fifth of a second, not quite a fifth, okay? And that's definitely the easier of these two. Because now, taking that same logic we just did in A, but realizing that the water is now leaking out, the load is going to be going down, and therefore the tension is going to be changing, and therefore the velocity is going to be changing. And so as this pulse travels down and the water is leaking out, we're going to have less speed. And so it should take a little bit longer. Now, just kind of as a rough curiosity, I don't think it'll take too much longer. So I'm probably thinking that I'll get some kind of speed like, 0.18 or 0.19. In fact, you can maybe give of a rough idea. If the water is leaking out at 700 kilograms a second, and we only have this many seconds for the pulse to go down. Now, this is where I'm making an approximation. So this isn't really the full correct answer. But just making a rough approximation, if I said the water leaked out for this much time, and remember, it's going to be longer than that, because it's going to take a little longer for the pulse to get down there. But let me just take that one, and I multiply it by 700. 125 kilograms of water would leak out. So if I take 1,000 and I subtract off 125, roughly, and like I said, it's going to be a little more than that because it's going to take a little longer than that, but roughly that water bag is going to have about 875 kilograms in it by the time the pulse gets down there. Now, like I said, since the pulse is going to be slowing down, it's going to take a little longer than that. So the truth is it's going to be even a little more than this leaking out. But this might be a rough calculation of how much there would be. And here's why I say that. If I multiply that by 9.8, by the time the pulse gets down there, the tension is about 8.575. And if I divide that by mu and take the square root, maybe we're looking at about 130, 131. So maybe down here I'll go velocity approximately at the end. And again, this is just kind of a ballpark, so maybe I'll just do the 130. I got really 131 here. But again, it is going to leak a little more water. So if I wanted to do kind of a rough thought here just to get started, it looks like when the pulse starts, it's traveling at about 140. By the time it gets down to the bottom, it's down to a speed of 130. So maybe that's roughly kind of averaging 135. Again, it's not a linear function, so this is not right. This is not the answer. This is just going to maybe give me a little better ballpark figure. I just know it's going to be a little bigger than that. So what if I did this? What if I took the 25 meters and divided it by kind of an average speed of 135 and 1.85. So my rough guess, because it's all based upon averages, which are linear functions, and we don't have linear functions here. But at the same time, we have, a function that changes as a square root, and it's a short amount of time. So, any function over a short distance is kind of straight. It's the slope there. So even though I call this a rough estimation, it's probably pretty decent. But that being said, let's get to the heart of the problem here. Okay, and I wanted to take all that time just to kind of give you a picture of knowing then, why I would have to do calculus here. So really what I'm saying is the velocity dx dt being the square root of tension over mu is a function. That is, I could do something like this. I could take the dx, put the square root of the tension over mu, and then move the dt to the other side. And this equation would be what you would call a differential equation, if you will, right? It's got a small distance it moves in a small microscopic time, and it would be a tension at that moment in time. So in other words, that tension right there is a function of time. And so to get the whole distance of 25 meters, I have to add up this dx from beginning to end. And of course, mathematically, if you add up from beginning to end, you have to do the other side of the equation also. And so the beginning is going to be time 0, because over here I'm adding up time, and I'll get to some total time. Let's see, I need a good symbol for total time. I don't want to use T for tension because it's in here, or capital T. And I don't want to use little t because that's the time for the clock running. So I'm kind of at a T. Oh, I'll go to the Greek letter tau. How about that? So letting the Greek letter tau represent my total time, this is how I'm going to get the answer of total time. I'm going to actually do this integral. I'm going to say that when I write out the equation for velocity, and this being a microscopic amount of time, and this being a microscopic amount of distance, in here there is a time on the clock, but the way I get total time into the equation, and that's really the crutch of the problem. I think if there's anything really hard about this problem, it's right here. How do I get the equation for total time? How do I get a variable for total time into this equation? Because when it's written without the integral and just the derivative, it doesn't have total time. It just has a time at a particular moment. A microscopic amount of time would make it move a microscopic distance. But we don't have total time unless you integrate. And so this integral is 0 to 25. And that, of course, is just 25. That's the total distance. And then this side is adding up velocity multiplied by total time. So we read 0 to total time. All right, so now it's a math problem. And of course, we got some calculus. But even before we get that, we should probably write, as we said, how does the tension change with time? Because we know it starts with this much tension. This is the 1,000 kilograms times 9.8. But then it is losing at a rate of 700 times t times the 9.8. See, because rate is always, some amount over time, right? So rate times time is the amount, and that's what I have there. A lot of times rate is speed, so speed times time is distance. And so this is how it would be leaking out. In fact, that's how I got earlier on. If you remember back here on the calculation, how I got right here, that there would be 875 kilograms left in the bag, I took the rate and right there, I took the rate and multiplied by a small moment in time to see how much would actually leak out. And I said 125. So then I subtract the 125 from the 1,000 to get 875. And so all of that I kind of did freehand is really this equation. Now maybe to just make my math a little bit easier in my calculus, why don't I do the t divided by the mu? Because the mu is the 1/2. So this number would be 1,000 times 9.8 divided by 0.5. So this would be 19,600. And this would be the 700 times 9.8 for the tension part of it, and then divide it by the mu, and I would have 13,720 T. And so that's the function of T, and then now I have to just do the calculus with the integration. So this, I guess, would look like this. So we got 25 on the left-hand side of this equation. And on the right-hand side, I have an integral from 0 to total time, which I'll represent with a Greek letter tau. And then I've got this function t over mu, which is this 19,600 minus 13,720 t. And I think I'll represent the square root as being raised to a power of 1/2. That way it looks like an integral that's pretty easy for me to do. In fact, it's just screaming u sub here. And so if I take my u and set it equal to the 19,600 minus 13,720 t, and my differential du now becomes minus 13,720 dt, I can then solve this by changing this to a u to the 1/2, and then solve for dt, which would be du over this negative 13,720 when I move that to the other side. And now this is a very easy integral to do, although it looks like we still got quite a bit of work to do. I'll start by just bringing the 13,000 in front. And then my integral becomes u, let's see, you add 1 to the exponent and then divide by that new power. Okay? And then I have the limits. And my limits I can put in here. And so I guess, why don't I put in my limits? I guess I didn't put them here on this integral. So when I change to a u, maybe I should put the limits of my u. It looks like, let's see, when time is equal to 0, if I put that into here, this would be 19,600 here. So 19,600 here. And then my upper limit would be the 19,600 minus the 13,720, and then that tau symbol, the total time. And it'd be okay if I don't write it on the integral. That's where that one would go. Okay, so those would be my limits. Maybe to save myself a little bit of calculator work, maybe I'll put that together with that and that. So let's see, it looks like in my calculator here, I already have 13,000. If I multiply by -1, there's the negative, okay. Now if I multiply that by 3/2, that's all the stuff in the denominator. Let me bring it over and multiply it by that 25. So all of these together make the negative 514,500 here. And then I just have to put in my limits of u to the 3/2 power. So this would be 19,600 minus 13,720 to the 3/2 power. Oh, shoot, I forgot to put the little tau in there. Tau to the 3/2 power. Minus 19,600 to the 3/2 power. Okay. And then, I'm going to run out of kind of space here on my paper. I'll leave this one alone. So 19,600 minus 13,720 tau to the 3/2 power. But I think I'll mess with this one here. This one here is 19,600 raised to a power of 3/2. Enter. Okay. Now, on this side of the equation, it's negative, but I'm going to move it over to here. Okay. And so I'll take it as a positive and then subtract this 514,500. And so all of this comes out to be 2229500. And should I try to squeeze it on or do the back? Yeah, I'll try to squeeze it in here. Let me bring this over to here. Okay. Now, I will raise both sides to a factor of 2/3. Because when I raise that to a 2/3, now it's just left with a power of 1. So this is equal to, yeah, I didn't give myself the right spacing here. Let me put the equal here. And so this is going to be 19,600, 13,720 tau. And then raising this side to a power of 2/3 is the other side of the equation, 17,066. And so now if you let me subtract 19,600 and then divide by that negative 13,720, I finally get total time. So there's quite a bit of math here. And hopefully you didn't make any math mistakes. Looks like it rounds to a 5. And there's my total time. And actually, surprisingly, it actually matches my rough approximations. So maybe my approximation wasn't too rough. But like I said, it's not correct to do this because you're treating it as an average and a linear function, and it's not a linear function, it's an integral. And it's much more complicated than that. But over this short period of time, any function, a square root function looks like this, right? It square root up like that. And over a short period of time, its slope is about the same as the shape of the function. So, and that's what happened here. It's just a short amount of time. But hopefully you did the integral. I'll give some reasonable points here to some kind of thought process of that. But this is the correct answer, and this is the hard one of the test. So hopefully that helped. And then on to the half question. It doesn't have a part A, part B. It's hopefully pretty straightforward. And it is a Doppler effect. It says a windless hot summer day gives the temperature. Dr. Young, I'm out riding my bike. I'm riding at this speed, but I'm being a road hog. I'm right in the middle of the road. So a car comes up behind me. And, of course, it's going to honk at me. Get out of the road, idiot. And here's the sound of the horn. What do I hear? And in this case, it's a Doppler effect. And I'll just write the Doppler effect. But if anything's hard about this, it's both the observer and the source are moving. And so the equation we have is the appeared frequency is the absolute value of the speed of the wave. So that's going to be the speed of the sound wave. Then we have the absolute value of the speed of the observer and the absolute value of the speed of the source. And whether or not we add or subtract or add from the original frequency is why we have this little bracket thing that we use the upper signs when they're moving toward. And so if the observer is moving towards the sound source, we use the plus sign. And then if the sound source is moving towards the observer, we use the minus sign. So that's why we put towards in the upper part to represent with the plus or the minus. And then we have the away. And again, if the observer is moving away from the source, we would use the minus sign. Or if the source is moving away from the observer, we would use the plus sign. So we have four combinations because we could have the two coming together, and so they would be both going towards each other, so we use the upper sign for both. I guess they both could be moving, let me get the angle same, so towards each other, away from each other, In my case, I have something maybe that looks like this. I guess I have the car and the bike. And the bike is moving away from the source. So I'm going to use the negative sign there for the observer. It's okay, moving away. But now the car is moving towards the observer. And so the towards going to be that upper sign. So to get this perceived frequency, I'm going to use a minus sign and get the speed of the observer. That's me riding the bike. And the minus sign for the source, because it's moving towards the observer, and the velocity of that is the 20. The frequency is the 420. Now, the one piece of the puzzle I am missing is the speed of the wave. And we have a temperature to work with. And so the speed, I guess you have two options. We have the more, rigorous equation for the speed of sound in air. And then we have its linear approximation of the square root, which actually just realized that was kind of our discussion back here, how a square root can have a Taylor series that can be reasonably approximate over short distances, and that's why our Taylor series is, these actually matched. Anyways, and so the Taylor series, or the approximation of this into a straight line, was our 331.5. Would it come out to be plus 0.607 t. So if I use the more rigorous equation for the speed, I would have 1 plus a 38 over 273, the square root of that, and times 331.5, and I would get a 353.8. If I have an approximation, I'm going to get slightly higher speed. Yeah, and so good. Should be a little higher. Approximation's always going to be a little mistake, and in this case, because it's a square root, it's always going to be a little higher. And so either one of those works. So I don't really, concerned about which one works or even the significant figures there. But as long as I did the more accurate one, let me put in the more accurate one into my formula. And so that 353.8 minus 9.1 is the numerator, and the 353.8 minus the 20 is in the denominator. And so now if I just go back and kind of copy and paste the two, okay, that's the quotient. And so the frequency is going to be shifted up by, it looks like about 3%. And then so I'll finish by multiplying by 420. And so 433, and maybe I should round it to 34 for 3 sig figs, although yes, technically there's only 2 there, 3 there, 3 there, 3 there. So I'll go with 3. So 434 hertz is the answer. All right. Hope you did well on it. Take care.